So this is the implementation of the modulation circuit. It is a bit of a mess, but this circuit is designed to take two signals at the input coming from the function generator. So the two input signals are coming from this channel and this channel. So if you can see, the second channel has a voltage of the input is 10 kilohertz, and then the first channel is 1 kilohertz. So this 1 kilohertz is the signal, and this 10 kilohertz is the carrier. So signal, carrier. So signal and carrier will be added together in the input of the circuit, and then an oscillator will be used to generate the output voltage. So signals come into the circuit over here on the left side. From there they pass on through the circuit and to the output oscilloscope. So if we observe the waveforms at the output, we can see that there is the pink signal and then there is the green carrier. So the pink signal will be modulated on top of the carrier waveform, and then that will amplitude modulate the signal. The amplitude modulated signal is visible below. So if we zoom out, we can see it something like this. This is how the amplitude modulation circuit would behave. So in amplitude modulation, we take a high frequency signal called the carrier and we vary its amplitude according to a lower frequency signal, which contains the information. This could be audio, for example. The key idea is that the frequency of the carrier stays the same, but the amplitude changes in proportional to the message signal, where the carrier frequency is much higher than the message frequency. On an oscilloscope, this appears as a high frequency waveform in the green and yellow, and the low frequency signal, as I said, is the pink one. So if you can see, the amplitude of the yellow signal varies as according to the pink signal. Amplitude modulation is the simplest and historically very important. It is used in broadcast radio, but it is also less efficient and more susceptible to noise compared to more modern modulation techniques. Still, it is an excellent way to understand the fundamentals of how information can be carried on a signal. That's it. Thank you. Welcome to the demodulation circuit. This circuit is made up of 5 low pass filters. So we have a high modulation carrier frequency and then we have a low signal frequency. So the purpose of this circuit is to eliminate or reduce as much as possible the carrier frequency. As the carrier frequency is high, we can use a low pass filter which filters out high frequencies to remove the carrier signal. The data signal in this case is a low frequency signal. So again, the high frequency signal is the carrier, low frequency signal is the data. So what kind of filter do we use? We use a low pass filter. A low pass filter's job is to allow low frequencies to pass and attenuate high frequencies. So in effect, what happens is that the high frequency carrier gets attenuated significantly while the low frequency data is able to pass through without much attenuation. Now, one set of filter is not enough because one filter will cause a small amount of attenuation in the carrier signal. But the ideal scenario is a brick wall filter. A brick wall filter is a type of filter which completely eliminates with a sharp decline. It eliminates the low frequencies and high frequencies. So basically, the more low pass filters you have, the closer you get to an ideal brick wall filter. In this case, we have gone for a fifth order filter. That means first order, second order, third order, fourth order, fifth order. So 5 set of low pass filters combines to get a fifth order filter. We can go on to a 7th order filter, 9th order filter, 12th order filter, and so on. The more stages we add, the more attenuation in the passband signal we will have, because there is no such thing as a perfect filter. But on top of that, the signal will be cleaned up. So the more signal attenuation we have for the carrier frequency, the cleaner the output signal will be. So let's take an ideal scenario where we have a brick wall filter. So if we come to the oscilloscope, we can observe that. So looking at the oscilloscope, you can see 2 signals. The top is the modulated signal. In this case, it is amplitude modulation. Amplitude modulation basically means the amplitude becomes bigger and smaller. So if we observe, The amplitude is small here, it starts to become larger, and it starts to become smaller. So this is the modulation, high frequency to low frequency. And then if you observe, this sine wave represents the change in the voltage as well. So when the sine wave is on the lower end, it is lower on the modulated signal as well. So move it closer, you can see that. So again, the top is the modulated signal and the bottom is the demodulated signal. So the modulated signal has amplitude variation while the data signal is causing that modulation. Then at the output we basically have one low frequency sine wave, and that is it when it comes to the demodulation circuit. This is one of the most basic demodulation circuits imaginable. But the downside is there will be extremely large amount of losses the more filter elements we add. So in this case, since we have a fifth order filter, the output voltage on the pink waveform is having a very small amplitude. So small that it might not be usable. Because this is a high sensitivity oscilloscope, we are able to measure it quite easily. But if it was not the case, it would be quite difficult to measure. So again, thank you.